Great. So we went through the first 5 topics of the second lecture, and I'm going to pick back up and discuss energy budget, dynamics, and rotation. And even though this is 3/8 of the lecture, I think this will go substantially faster than, say, for example, the discussion of composition and things like that. Okay, so let me just scroll down and find where I need to pick up. Okay, so I'm going to talk about energy budgets and dynamics, and in some of these cases I'm going to talk about them at the same time because these are coupled things from an observational standpoint. And so I'm going to start this discussion with WAS-43, this spectroscopic phase curve observation that's been done. I talked about the idea of phase-resolved observations yesterday, especially for tidally locked close-in exoplanets. This has been done in photometry, especially with Spitzer, since 2007 or so. But a recent breakthrough is the ability to do this not just in broadband photometry, but in spectroscopy, which hopefully I've made the point is much more powerful. So this is a summary of the observation that we did actually for WAS-43b using Hubble. This is quite a lot of HST time, 41 HST orbits over 3 days of the planet, seeing 3 full orbits of the planet. So this is the characteristic sinusoidal variation you expect for a hot Jupiter, observing from the cold night side to the hot day side, and then back to the cold night side. And so just to give you a sense of the size of the scale, the transit is off the scale here, 3% transit dip, and a 400 ppm phase curve variation comparable to the secondary eclipse depth. This is the white light curve all bent up, but the exciting thing is their ability to do spectroscopy. That didn't work. Which is illustrated here by this movie. And I want to say this is not a theoretical prediction. This is a movie based on real data. It's been smoothed, but we have something like 15 points in wavelength and 15 points in orbital phase. And so we smoothed to make this movie. And the idea is that using spectroscopy, you now resolve molecular absorption features that allow you to be certain where you're probing in the atmosphere and retrieve abundances in the thermal structure. And also to diagnose how the energy is being redistributed or not from the day to the night side. Previous observations of these kinds of planets in photometry revealed discrepancies between the data and the models. But here with spectroscopy, we can diagnose that much better. For example, we can rule out non-equilibrium chemistry. We can rule out high C/O abundances and things like that. And so we can say, for example, if these data are discrepant from the models, then it has to be something other than a compositional, for example, problem. Question? No, that's just to make the movie. Yeah. So what we have is longitudinal information, and each time we observe the planet, you're observing the full hemisphere, and you can deconvolve that into longitudinally resolved information, but the latitude you still don't have. That requires eclipse mapping, as Laura talked about yesterday. So we confronted this particular data set with GCM predictions from Tiffany Kataria, Adam Schoeman, and collaborators. And this is just an example from one of their GCM runs. Latitude, longitude, this is a slice at around 0.1 bar. Temperature is the color bar, and the arrows show the wind's speed. Both the direction and size of the arrows give the wind speed. And you see the models predict the emergence of this equatorial superrotating jet, hotspot offset. And these, the data, the models are remarkably consistent with what we see for the day side of the planet. Here's the day side spectrum of the planet measured at secondary eclipse, and then the model predictions. And so these models have obviously many fewer knobs to turn in them than 1D models do. These are more first principle calculations. And you can see the remarkable agreement with the nominal models, slightly enhanced metallicity models match the day-side spectrum really well. Where the models fail to reproduce the data is over-predicting how much energy, well, not over-predicting how much energy, over-predicting the flux that we're measuring at the night side, right? Because that's the observable. We measure the flux. We try to deduce how much energy is being transferred from the day to the night side. Because we have spectroscopy, we can rule out a whole host of things like non-equilibrium chemistry, C/Os, and thermal structures that would give rise to this sort of discrepancy. And the current leading explanation for this discrepancy is the presence of clouds on the night side of the planet. Now moving into, well, does anybody want to talk about this first of all? So this is really all I'm saying in terms of phase curve observations. Phase curve observations have been done for a number of other planets, like I said, in photometry. And so from that, you can deduce constraints on the albedo and recirculation. In photometry, you have to make some more assumptions than you do with spectroscopy about these things. But I would say these are fairly reliable inferences if the data themselves are reliable. So this is a plot from one of Nick Cowan's students from last year showing the confidence interval on the deduction of the albedo and recirculation for a few of these hot Jupiters that have been observed with phase curves. Here's WASP-43, which we've done spectroscopic observations for, and so we're probably a little more robust than the others, but good quality data on with Spitzer photometry on a few of the other planets. And so I'd say this is a pretty big mystery why this spread here. There seems to be no trend. There's no trend with temperature in these. There's a divergence in properties. Why is WASP-43 so very different from WASP-189? It's not WASP, HD 189.733. It's not obvious, why that should be. So this is, sort of purely an observational result that's looking for a theoretical explanation. There's been interesting work by Adam Schoeman and his collaborators, and particularly most recently from Tad Komacek, looking at how redistribution should depend on equilibrium temperature. I think this was described in the talks, the lectures earlier this week, the physical effects that could happen here, in particular, perhaps something like the radiative timescale compared to the effective timescale and wave propagation timescales probably play a role. There should be a trend of higher redistribution, so that's the y-axis here, is a function of equilibrium temperature. There should be a trend towards more redistribution towards colder planets, and it's perhaps not perfectly accurate to say this radiative versus advective timescale argument, but I think that works kind of heuristically. These really hot planets have very fast radiative timescales, and so they can re-radiate the energy faster than it can be moved to the cold night side. But the pattern doesn't really exist in the data as we see them now. You have planets that are hot but show fairly good redistribution at certain wavelengths. You have planets that are cooler or have lower equilibrium temperatures but no redistribution. These are figures from a paper from Kevin Stevenson that's going to be submitted soon. Really the focus is on WASP-43, but pulling together all these data from the literature. Kevin has proposed a different trend, and you may see it by eye, which is that the redistribution function could depend on the orbital period. And the orbital period here is a proxy for the rotation of the planet. Kevin has written a Spitzer proposal that I read, but where he outlines what his hypothesis here is, but I have to admit, frankly, that I don't remember all the arguments here. So I'm just going to put it here and say, wait for this paper, which should come out on the archive, I think, quite soon, just within a couple of weeks, if you want to read about his idea here. But this is obviously still a developing area and trying to understand how the energy is being redistributed from the hot to cold night sides. These are all hot Jupiters, but recently there's been the result from Brice Demery and collaborators looking at thermal phase variations with Spitzer of a super-Earth. And this is 55 Cancri E, orbiting a very bright star, very highly irradiated super-Earth, roughly 2 times the radius of the Earth in size, equilibrium temperature on order of 2,000 Kelvin, maybe even higher. This is a very difficult measurement to understand because you see what's going on here. So this is the secondary eclipse. You see minimal redistribution. No, wait a second. There's strong redistribution. Oh, what's the problem? There's strong redistribution from the data of the night side, and then a large offset in the hot spot. This is especially difficult to reconcile with the composition of this planet's atmosphere that was inferred from the transmission spectroscopy that we talked about for this planet from the UCL group. And also I'll point out the 55 Cancri E, or 55 Cancri the star, just as it's a difficult target for HST with C3, it's also an extremely challenging target for Spitzer. It's a very, very bright star. These instruments were never designed to look at stars this bright. And making use of all those photons you're getting is extremely difficult in the face of the strong systematics. Talking now about the energy budgets of directly imaged planets, I'm throwing this figure up here, and I'm not really an expert in this area, but I did find it extremely interesting. This is a plot for a directly imaged planet Beta Pictoris b, where they've taken GPi spectra, inferred the surface gravity and the effective temperature of the planet, and then used that to compare with evolutionary models where they try to estimate the mass of the planet and also the initial entropy of the planet. Remember, these directly imaged planets are young and are still releasing the heat, significant heat of formation. And so the initial entropy of the planet plays a big role in how much heat these planets have to give out. I thought this was really interesting, trying to put confidence intervals in this sort of 2D parameter space based on the spectroscopic characterization of the planet. This is a paper from a few years ago, and I haven't seen this done since. Maybe I've missed it, but maybe also there's something fundamentally wrong about this. I was surprised it didn't get so much attention because I thought this is a really exciting thing to try to do, to try to constrain the formation of the planet. Is there anybody in the audience who's an expert in this and who wants to comment? Okay, well, maybe I've taught Jonathan Fortney something.
There were suggestions in the past to do this. I don't think I saw this plot either.
This is from the Sphere team, but analyzing GPi data, GPi commissioning data for Beta Pic B.
It's really tricky. The entropy, you've got to get 80 maps, right? So you've got a temperature profile, you have to retrieve a temperature profile, lead just where you're looking on the 80 maps.
Right. Cool. Yeah, so I thought this was really interesting, so I'm glad I shared it. Maybe some people hadn't seen it. Okay. So returning back to the question of dynamics, one of the powerful things that high resolution spectroscopy from the ground can do, we talked about revealing molecules that you can't see with existing space-based instruments. But another thing that you can do is actually probe individual line shifts and line shapes. We'll talk about line shapes in a minute, but now I want to talk about the shifts. The Doppler shifts of the spectral lines themselves indicate the presence of winds in the atmospheres of hot Jupiters. The first result in this area was by Ignace Snellen in a paper in 2010 looking at HD 209458b, CO absorption and transmission, and seeing a 2 sigma evidence for on order of kilometer per second Doppler shift in the CO lines, indicative of wind speeds in the planet's atmosphere. This 2 kilometers per second is the right order of magnitude, and so this is really a nice result. It was only 2 sigma significance, although it ended up being in the title of the paper, which is always interesting, as someone who's kind of a stickler about statistical significance. More recently, I think we have Tim Loudon. Is an audience, Tim? Tom, thank you. T, yes. Nice to meet you. You have a great paper interpreting the observations, HARPS observations of HD 1899733b, looking at the sodium line, and actually a reinterpretation of the Wittenbach result, which I thought was really great. Not just looking at the Doppler shift of the line, but perhaps detecting different wind speeds on the leading versus trailing limbs of the planet. So that's what's represented here. It's a really nice paper. Talk to Tom about this if you're interested. I think this is really, pointing out the power of this ground-based high-resolution spectroscopy, doing something that no other technique can do, seeing these Doppler shifts and directly measuring the wind speeds that we've been trying to infer from observations of phase curves. Yeah. Do you have a sense of the pressure? Good. In addition to measuring the Doppler shift of the line, you can also measure rotational broadening of the line. So this is the width of the line as it's being changed. And not a single line in this case. This is back to CO and H2O lines. This is a paper on 1899733b by Matteo Brogi, observations with CRIRES, seeing H2O and CO, and looking at the width of the cross-correlation function and modeling that and trying to deduce the rotational, the v sine I of the planet. This is it's interesting for HD 189733 to try to measure the rotational velocity because we know the size of the planet and we know its orbital period and we assume it's tightly locked. So we really should already know the rotational velocity of this planet from other means. And so measuring it gives us sort of a sanity check on our assumption about tidal locking, and then vice versa about being able to pull this information out. And so it talks here in the caption about their constraint on the rotation period and how consistent that is with the orbital period. The orbital period is 2.2 days, if I remember correctly. And so they get something perfectly consistent with tidal locking in the orbital period of the planet, which is really neat. Using the same technique, but combining with high contrast imaging, Ignace Snell and collaborators observed beta pic B and were able to deduce a high v sine I for this planet. And this is really cool because this is a planet that we have no idea what the rotational velocity would be from other means. This is not a tidally locked short period planet. This is a distant planet that's just sitting out there. And so this is a really amazing result, measuring a high v sine I think on order it's 25 kilometers per second. And then they made this interesting figure which plots equatorial rotational velocity. You have to make some assumptions about beta pic B, but compared to the mass of planet and putting the solar system planets. And surprisingly, in log space, it kind of lines up, suggesting a power law relationship. And then you put beta pic B on there, and it also fits this trend. I'm not sure the physics explaining this is particularly strong. It's sort of an empirical relationship, but it's certainly interesting to think about. So this is not 2 Jupiter masses. This is 10 and 100. So he put field brown dwarfs on there, I think. And what would be the problem with that? Well, they have a distribution of I's, right? You measure for a star, V sine I, or brown dwarf, V sine I. And so they have a distribution of I's. And then some of them may be in binaries. I don't know. Different formation mechanisms, of course, right? These are objects that formed probably from direct gravitational collapse. I don't know, are there, as it said?
The problem with the brown dwarf stuff, we've done some unpublished work on this. It depends on how you treat the pressure broadening and the rotation rate. Where you're looking, depends on how deep you're looking in the atmosphere. There's an additional axis of uncertainty, pressure broadening.
Right.
Yeah, I'm always a little skeptical. Maybe I shouldn't be.
I think the stronger comparison for this plot was, though, with the comparison of the solar system. That was what he was trying to make. And I'm not really... Okay. Right, yeah, there are some assumptions that have to go into that. So what you measure is the width of the cross-correlation function. And there's a lot of steps between that and the v sine I, and then more steps between the v sine I and actually the projected equatorial rotational velocity. So I think this is my last slide. Yes, this is my last slide for the observational summary. So I don't know if we want to have questions about that. I open the floor for questions. Yeah. Which,
One where you showed like a better correlation.
This one.
Yeah, so when you write temperature.
These aren't albedos.
No, I know.
Yeah, okay.
In the top plot, you have a EQ. Does that take into account the inferred albedos?
No, it doesn't. It's probably assuming a uniform zero albedo.
Maybe if Gloss 33 had a lower albedo.
Well, we know the albedo, or we have a good handle on that because we've measured the flux all the way around.
Yeah,
so we have a good. The albedo is very low.
Yeah, so then it's right.
Well, then, I mean, equilibrium. This is the problem with equilibrium temperature. It's like the day side temperature is almost 2,000 Kelvin, and the night side is below 1,000. So what's the characteristic temperature of this planet? Like, what do you use? Tad, do you have any thoughts about that? Did you also assume 0 albedo when you made your version of this figure? Well, yeah, for Waltz 43 especially, it's this, right? You can make that plot as a function of equilibrium temperature, but what it comes down to is the predictions of the GCM are that you have detectable night side flux, and we see nothing. And so our interpretation is likely what we're seeing are thick clouds on that are obscuring. This is not transmission, right? But in the emission spectrum, we're seeing a very high altitude because the optical depth of the clouds is pushing us at the lower pressure, and the temperature is lower there. So there's probably energy being pushed around, but it's at deeper levels than we're probing. So put clouds in GCMs. Easier said than done. Uh-huh. More comments and questions? You guys just love hearing me talk, so you just want me to keep talking. Okay?
So, yeah, the other thing,
Yep.
the rotation rate, so it could have had it's on that plot.
You might have.
Yeah, so like,
I guess he doesn't have Mercury. Doesn't have Mercury in Venus.
so what I'm saying is, like that, yeah, it's sort of silly to make a plot and then draw up.
Yeah, but at least you have some physics. I mean, you can say the rotational velocities of Mercury and Venus are strongly influenced by tidal effects. Like we know that, right? So we're trying to see like what's, for things like Earth and Mars and Jupiter and Saturn, we're seeing the primordial rotation periods, velocities of these objects. I mean, so I could support what he's done there. That's right. I think it's 2.2. But the error bar is consistent at 1 sigma with 2.2, I think. This is just for this figure. What's the best fit? The best fit may be something like 1.7, but the error is pretty large. Yeah.
So then, I mean, you're not actually. I don't know if you're actually
Well, this is the actual broadening of the line, not the Doppler shift, right? So can the winds?
But I just mean like if you have a belt in the middle that's a little bit rotated, then that would rotationally go up. Unless it was going too fast.
The question is, is the region of the planet with that, right? The thing when you're talking about a planet, you got this disk, and it's like one whole half of the planet's going, and the other half, right? So you've got the whole disk versus whatever the width of this band is. Yeah. Okay, that's a good point, that it's not trivial. It depends on the ratios of the areas and the temperatures and what the flux weighting between those parts of the planet. Yeah, this is, yeah. More thoughts, Andrew? Mm-hmm. 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 Yeah. That's a great question. It reminds me of a figure that I could have put in here For the observation, the spectroscopic observation of WASP-43 phase curve, since you have the spectroscopic observation, you can sense what the temperature is at different altitudes, and you do that all the way around the planet. And so there was a figure in Kevin's paper presenting those data, Stevenson 2014, where we detect a difference in the hotspot offset as a function of pressure in the atmosphere. It's not super strong, but it's consistent with the expectation that the hotspot is shifted left to deeper, lower altitudes, higher pressures. So that's sort of the first result in that area. And I think this has been done for brown dwarfs, so that's, it's a bit different for a highly irradiated planet versus a self-luminous object. Now we'll never push down deep into the atmosphere, right? The continuum, even in an emission spectrum, is still pretty high in the atmosphere. But we have hints of that slope already, that there's a altitude dependence in the hotspot offset. Yes. It's a supplementary figure in Kevin's paper if you go dig that out. Okay, cool. So let me close this and open the next one. So, the future, with an exclamation point. So this will be a shorter lecture, and so I think we'll definitely get through. We have a little bit less than an hour. I think that'll be pretty straightforward to get through. As promised, I'm going to begin with some open questions, and then I'm going to talk about upcoming facilities. And my discussion of upcoming facilities will not be completely comprehensive. In some cases, I'm choosing just examples of representative instruments and things that are being conceived and perhaps built. But hopefully this gives you a sense of the things that we expect to come on a number of different timescales. Well, let's start with the open questions, and let's go back to the question that we got earlier this morning about how to derive abundances from transmission spectra in the face of model degeneracies. And so, we could have a little discussion about this because I think this is a really important question. As we go to smaller planets, typically we're probing lower temperature objects. And lower temperature objects become worse and worse targets for emission spectroscopy. Emission spectroscopy doesn't have that same degeneracy as transmission spectroscopy. And for me, that's why it's been my favored tool for deriving absolute molecular abundances. But in the regime of planets where we're only going to be able to use transmission spectroscopy, we're still going to want to get that information. And so I think an open question is how exactly we're going to do that. And so I show here a figure from one of Bjorn Benecke and Sarah Seeger's papers from a few years ago, which kind of gives a really nice sort of didactic description of what information uniquely can be extracted from transmission spectra. And so he's got this figure where he illustrates, a model transmission spectra and shows these things he's talking about color-coded and then matches them up in this little diagram here on the right. A common thing that's being pursued these days is the search for molecular Rayleigh scattering in the blue optical. The point being that the Rayleigh scattering gives you a unique constraint on the scale height and sets the pressure level that you're seeing. So if you measure some molecular feature in the infrared relative to this Rayleigh scattering slope, you can get the pressure level and thus derive from the partial pressure of that molecular species the absolute abundance of the species. So that's something that's being pursued, and I haven't seen this actually work yet, although a lot of effort's gone into it. A challenge is that often the Rayleigh scattering slope here from, you're hoping that you're seeing H2 Rayleigh scattering in a giant planet, that this is obscured by the scattering from clouds. So clouds complicate this picture because you've introduced an additional chemical species and an additional uncertainty in the pressure level. And so even if you see some scattering signature, you've added new information, but now you need to derive more information. And so you kind of lose out there. The point being that if you measure this methane feature relative to the scattering slope and it's a haze scattering slope, it doesn't give you really any more information about the abundance of the molecule. So I want to just draw your attention to some of the other diagnostics in this plot, and also particularly in the context of future facilities. High precision measurements here in the optical are most easily done with HST right now, with the STIS instrument. And we've been trying to see these Rayleigh scattering signatures, and it's not really been working out super well. Part of the reason could be that the precision is just not there, and so we'd like to get better precision. but our future facilities aren't going to be covering these wavelengths. James Webb Space Telescope, which I'll talk about in a minute, only will go down to around 0.8 microns in its wavelength coverage. And so you're going to get all this rich stuff in the infrared, but without that Rayleigh scattering signature, which has so much potential. And so there's other things going on here that I just want you to think about. If this is a problem you're interested in, I invite you to take a look at this paper and consider the size of these different diagnostics that are in the spectra, and particularly in the context of a spectra we might get with JWST. I hope that answers your question. Good. Another question that I've been thinking about lately, and it's come about because of my work with Jonathan and Mike Line and Kat Fang, who's in the audience. Kat, hey, yes, I'm showing your figure. I hope it's okay. And that's the issue of these planets are often modeled with 1D models, not just forward models, but our retrievals are all done in 1D. But planets are, first of all, spheres. And second of all, for transiting planets especially, they're going to have very inhomogeneous temperatures, not just from the day to the night side, but from the equator to the pole, and then different leading edges. The leading and trailing edges of the planet are probably different. And so this is a new result from Kat's paper that's been submitted, where she's looked at existing data for WAS43b and asked herself whether the assumption of a 1D retrieval could not be superseded by having a retrieval with multiple temperature components. So the idea here is you do a 1D retrieval with one temperature pressure profile. I think that's the reddish orange TP profile derived here. And then also a retrieval where she says, and this is at a phase where you're seeing half the day side and half the night side, 0.25 or 0.75 would work. Or saying, okay, well, we know there's poor redistribution on this planet, or rather we see a much hotter day side than night side, much more flux in the day versus the night. That should be represented by two different temperature pressure profiles. And so that's the purplish blue color here. And you can actually see evidence for this in existing data. And the evidence comes from the fact that if you look at this spectrum and you model it just with 1D, you get a strong detection of methane absorption, which is totally unexpected at these temperatures for chemical equilibrium. Now, for me, when I see something out of equilibrium, my first assumption is the data are wrong or the modeling assumptions are wrong. In this case, it's probably the modeling assumptions, because when you use two TP profiles to model the data, you get something more like you expect, just an upper limit on the methane abundance. And so this is, for me, actually, I think this is pretty good evidence that we need to start thinking about these planets, not just in terms of 1D, but having multiple components, especially when you're seeing them off, say, the day side phase. Questions about this? Another thing that could be a complication is something that Mike Line and Vivian Parmentier have thought about, which is that you could have differences in the leading and trailing edges of the limbs of planets because of different temperatures, and that could lead to different cloud formation on these limbs. As a reminder, in transmission, we're seeing the transmission from the whole limb of the planet, which is a much more inhomogeneous thing, I think, than, for example, looking at the day-side emission, which is probably much more uniform. And so they did some calculations saying, well, what happens if one of those limbs, one part of the limb, say the leading edge is cloudy and the other is not? How does that influence transmission spectra? And it turns out it just makes the degeneracies worse. Thanks a lot, Mike Line. But certainly we want to make much more accurate inferences, so it's good that they've thought about this. And so I just refer you to this paper. They've done some comparisons of these models with real data and shown that perhaps for some planets we could actually, if we get a little bit better data, we could distinguish between these different models. And so that's an interesting thing that may be done over the next few years. Okay, so I've talked about open questions as part of my introduction to talking about the future. But I want to kind of loop back around to yesterday morning, which you all remember super well, and talk about this introductory slide. And I said there are really, I think, about two fundamental questions, categories of questions for exoplanet atmospheres. What are they like? Where did they come from? And so I've shown a lot of individual results for planets. And that's kind of where we stand today, I think. Progress has been made to establish robust measurement techniques robust interpretation techniques, but a lot of it's being used on individual planets. As I said earlier this morning, the strength of exoplanets in this game is really the numbers, or one of the strengths is the numbers. And so I think moving from these sort of boutique observations of individual objects to large-scale studies, applying these techniques that we've honed over the last, let's say, 15 years since the study of exoplanet atmospheres began, and doing comparative planetology is really the thing that we should be moving towards. Furthermore, not just in the question of giant planets or Neptune-type planets and things like that, atmospheres play a key role in the habitability of terrestrial planets. And so that's obviously a key question that's going to be on our minds as we move to the future. As we start finding these worlds, terrestrial planets, in the habitable zones of stars, we start asking ourselves, how are we going to get spectra to diagnose the atmospheric composition, mass, temperature of these worlds, and perhaps to look for the existence of biosignature gases that are evidence of life. So I want to start with this discussion of comparative planetology first. And I want to go back to sort of like more mainstream exoplanet science, which is sort of centered on characterizing frequency of planets, properties of host stars, stuff that's a lot easier than what we're trying to do, right? Those guys are taking the short way out. Anyway, I'm just showing a couple of interesting results in this area of planet frequency and characterization of stars, and combining those and using the numbers of exoplanets to their fullest advantage. This is a result you're probably all familiar with. It's the planet metallicity correlation, showing that giant planets are much more common around stars that have high metallicity. This is, I think, one of the most fundamental results in the field of exoplanets, right? And so this is because of the power of numbers that we have and the diversity of planetary systems, the diversity of stars that planets can be found around. And then also, this is a plot from one of Jonathan's students from a few years ago. I think you have an updated version of this. This is the one I have. Looking at inferences of the heavy element mass in planets based on their measured radii and comparing that to host star metallicities and showing a trend here. I think here the normalization is not really known. I think you may assume like 10 Jupiter masses of heavy elements for Jupiter, 10 Earth masses of heavy elements for Jupiter. But anyway, you see the trend. The trend is the more important thing. You have more heavy elements inferred from the radii of these objects as a function of stellar metallicity. The point is not this stuff, but the point is saying this is the kind of thing that we should try to do with atmospheres, right? We should start looking at atmospheres as a function of all sorts of different properties. And so I just list a few of these things that we'd like to do, right? We'd like to know, ultimately, planet mass, radius, atmospheric composition as a function of a whole host of different properties. That's not something that's going to happen tomorrow, right? But this is the thing that we should be driving towards. And so as we start thinking about future facilities, you may think I'm going to jump immediately to the discussions of JWST, because that's obviously the thing that's looming on the horizon. But I first want to ask ourselves the question, do we have enough planets to do this kind of comparative planetology? Do we have the tens, hundreds, or even thousands of planets that we'd want if we could take spectra of those objects? Do we have enough? I showed an earlier version of this diagram today, radius, mass, and it was limited to planets with high precision measurements of these quantities. Here's the version of the figure with just everything that we know, right? And it's a total mess, right? The handful of objects that we have high precision measurements for, especially for the small planets, is low, on order of 10 to 15 objects. Certainly not a large enough sample for comparative planetology with robust statistics. Incorporating all these ones with low precision measurements, maybe we have enough objects, but the precision on the masses and radii are not high enough. So we want to know the masses and radii because that's, for transiting planets, that's the opportunity that we have, is to have that information. But it depends on a whole host of other observations before we start doing the atmospheres. Transit discovery, radial velocity measurements. And so I want to talk about just a minute about the TESS mission, which you've probably all heard of, but I can show a few slides about that. The problem with this diagram is a lot of these objects here in gray are Kepler discoveries, which are wonderful for assessing the frequency of objects in terms of their size, but terrible for doing comparative planetology in terms of bulk compositions of planets and planet densities. Because the stars these planets are orbiting are too faint for ground-based radial velocity measurements to measure their masses. The problem is Kepler has found thousands of planets, but if you talk about planets around relatively bright stars, it's a small handful. So this is the motivation behind the TESS mission, is to do an all-sky transiting planet survey to look for transiting planets, and especially small transiting planets, around the bright stars that we can measure radial velocities for, and that are also amenable to high-precision spectroscopic characterization. So this is just a summary slide. I've added this breaking news to this slide that I got from Josh Wynn. The earliest launch date for TESS is now set to December 2017, so about a year and a half from now. And then TESS is doing all sky, but one hemisphere at a time. So the first year of operations, it will do the southern hemisphere, and then it will turn over and do the northern hemisphere. I've got some figures on that stuff. Let's just skip through that. TESS is doing all sky. TESS's coverage of most of the sky will be very short relative to Kepler's, the Kepler prime mission of the Kepler field. Most of the sky will only be covered for 27 days. That's fine from the standpoint, I think, of atmospheric characterization for the most part, because I don't see atmospheric characterization of planets with longer periods than that being particularly a big industry in the future. At the, I don't know if this is the ecliptic pole. This is the ecliptic pole. At the ecliptic poles, both north and south, there will be overlapping fields from TESS's observing strategy that give very long coverage. And so these are the parts of the sky where you're expected to find transiting planets potentially in the habitable zones of their stars. And so this part of the sky, you will find a few planets in the habitable zones of M dwarfs, terrestrial planets perhaps, and these may become really special targets for JWST spectroscopy. In terms of numbers, there will be lots of transiting planets found around bright stars that are amenable to radial velocity measurements for masses and atmospheric characterization. In terms of habitable planets, it's not going to be a huge number around bright stars. Those objects are common, but not so common that you're going to find them around very bright stars. They're almost all going to be found around mid to late M dwarfs. This is a plot from a simulation paper by Peter Sullivan and the TESS team. Came out last year, showing expected TESS discoveries based on Kepler mission statistics in terms of their host star effective temperatures, and then those planets with insulations similar to the Earth. And so you can see the small planets in the habitable zones from TESS will be around mid to late M dwarfs. And those are intrinsically faint stars, and so those are challenging from radial velocity measurements as well. Yes? Yes, yes. So this is not an extrapolation. There's no extrapolation because this parameter space is very well covered by the Kepler mission in terms of planet size and orbital period. Probably where it's weakest is in terms of stellar type, but it's still not an extrapolation. This is purely covered by the Kepler mission. So I'd say this should be fairly accurate. Yep. And so it's interesting to look at the number of these small objects with Earth-like insulation and the magnitudes of the stars. It's not a lot of planets, but these are within reach of radial velocities, and these are within reach of JWST transit spectroscopy. So that's an exciting future from the TESS mission. Okay, so let's talk about JWST. And, oh, yes, another question. Eric. M dwarfs. Mm. Yeah. Yes.
I think for the rocky planets, the level 1.5 Earth
yeah, that may be true. So you may be on the edge for the very habitable planets, like the less than 1.5 and around the mid to latest M dwarfs. You might be on the edge of what Kepler has done. So that's true. That's true. That's a good point.
I think specifically we don't really have much evidence that we know there are lots of true Earth radii planets. Those have massive envelopes underneath that.
Yeah. Yeah. Yeah.
We don't know whether the rocky planets we have close to right now are all representative.
That's true. That's true. Okay, that's another good point. Yeah. Right. Right. Yeah, absolutely. We're trying to find those planets around brighter stars so that the radial velocity measurements are much easier. And so that's really the limitation. That's this figure. And I chose this, sorry, how far back do I have to go? I chose this on purpose, right? Like I made it look as bad as I could make it look, right? But the point being that if we find the analogs of these planets just around the brighter stars, which you can do with an all-sky mission, then the radial velocity measurements become much more feasible. And so I think there's work being done on that, but I think we're approaching the end of what's really possible. I think people have exhausted the list of planets around bright stars. So those are the colored points that are underneath all those gray points. They've exhausted the list of those that have come from Kepler. And beating down on these ones in the gray is just not really, it would take forever. So you're not going to get the telescope time to do that. And so the gray ones are probably not going to get much better. We're going to have to just throw those out, basically, and start new with the test planets. Yes? That will definitely help the case of measuring the masses of the planets around the mid to late M dwarfs. Absolutely. Eric, you have another question? Well, I don't know if K2 is going to give you a lot of TTVs. The time coverage is not great. Just like I don't think TESS is going to be a strong TTV mission, right? That's true. Absolutely true. Yeah, and yeah. More comments and questions? You guys want to talk about JWST? JWST. Man, there's a lot of bad stuff going on in the world these days, right? You got like Donald Trump. You've got, less funny than that. You've got mass shootings. You've got countries leaving the EU probably. But man, if there's nothing that's going to make you feel better about humanity, right? The James Webb Space Telescope. Holy shit, right? 6.5 meter space telescope. They coat the mirrors in gold, for God's sake, right? Like, hell yes. So hopefully this is a sentiment that you all share. We eagerly await the launch of the James Webb Space Telescope late in 2018. JWST will revolutionize the area of transit spectroscopy because of its large collecting area to achieve higher precision measurements, its broad wavelength coverage with multiple instruments and multiple modes. You can see I'm getting really giddy here. And much higher spectral resolution. Uninterrupted observations. Man, I'm just like going crazy here. And so I'm not going to go over all the things that JWST could do. I'm going to just point you in the direction where you could read more about this. There have been some papers coming out recently that kind of describe more rigorously than had been discussed before the different instruments and their applicability for transit observations. And so this is a figure summarizing JWST instrument capabilities from Kevin Stevenson, a white paper that he put out with a large number of people from the community. Also, there was a workshop hosted at IPAC 2 years ago now by Chaz Beichman, and then it was a paper, a conference proceeding, a conference discussion that came out of that describing the different instruments and modes and the current thinking in the community about the right way to pursue different observations and things like that. I just want to remind you that for the vast majority of the instruments and modes on JWST were not designed to do this stuff. And so we're going to have some hard work in front of us to optimize the use of these instruments for our observations. Some of the instruments and modes are probably not suitable. For example, some of the MIRI observing modes use, I think, an IFU, and I just think that's a terrible idea. So, for example, our ability to make high precision measurements, spectroscopy in the mid-infrared is not going to be great, not to be a downer. So, I just want to add a dose of realism here. All that stuff I talked about yesterday, not all of it, but a number of the things I talked about yesterday are relevant for JWST. So let's not just sit on our laurels and say, JWST, when we come, is just going to spit out beautiful spectra, right? We're going to have to do some work. Tying back into this question of how precisely you can get abundances from transmission spectroscopy, and also, even emission spectroscopy, just point to a cool paper by Tom is his first name, right? Tom Green? Tom, yes, Tom Green, also including Mike Line and others, looking at JWST simulated spectra in the photon noise-limited regime and doing retrievals on observations with various instrument combinations and things like that. And you can see that extremely precise molecular abundances and constraints on C/O ratios and metallicities and things like that, even in the face of cloud degeneracies, can be obtained. I think there's still a question of how you optimize your instrument selection and things like that, but for sure this is a really exciting thing that we're looking forward to. The capabilities will be amazing if we can get the high quality data out. This is another figure from Tom's paper riffing on Laura's result for WAS43, metallicity as a function of mass. You're tired of hearing me say this. Here are error bars for the kinds of measurements you could expect to make for JWST using various instrument combinations. These aren't points on the figure. These are just representative error bars. You can imagine populating this relationship with those error bars, with points with those error bars. Probably combinations, yeah, instrument combinations. So black for nearest, near cam, MIRI, blue for just nearest and near cam, red for nearest. These are probably transit observations. Transit, Mike is nodding, great. These are transmission spectroscopy observations using different instrument combinations. So that's different wavelength coverage and things like that. In terms of smaller planets, habitable zone planets are probably going to be on the edge of what JWST can do. This is just a recent simulation by Joanna Barstow and Patrick Irwin for the TRAPPIST planets, planet B, C, and D, although you don't know the period of D. Anyway, these are simulations of many JWST observations over a wide wavelength range, showing very challenging detections of spectral features for these Earth-sized planets. So while comparative planetology should be very straightforward with JWST, for larger planets, pushing into the habitable regime, I think it's going to be extremely challenging. And so, it's a big question how that's going to play out versus allocation of observing time and things like that. The timeline of JWST, even though it's a few years away, there's a lot of stuff that's going to happen over the next 2 years. And I want to highlight this idea of a so-called early release science program, which the community is trying to get behind. This is talked about in Kevin Stevenson's recent white paper. The point being that we don't know the performance of JWST, and we don't know the right combination of instruments. There's almost an infinite combination of instruments and modes that you might try to use. And so one thing that we hope to do is convince the Space Telescope Science Institute to do observations of a small select planet or a couple of planets with a variety of modes so that the community can develop techniques for analyzing the data and also identify the best modes for addressing specific science questions. So Kevin has done a study of what's the best planets to look at. And so he's done this in terms of JWST's visibility during the year. We have an expectation for when JWST will launch, but that's 2 years from now. Things will move around. It'll probably be later than earlier. And so we want to be able to do these observations as soon as possible when JWST is up there and operational. And so it actually becomes a question of months of whether you've picked a certain target for these observations. And so in his paper, he describes how he's gone through and tried to select targets. Of all planets, WAF62 seems to be the best one that we should look at. Right? Crazy, but there it is. So I invite you to read this white paper if you're interested in this idea of the early release science program. We all know about JWST, but will there be science to do beyond JWST in this area? And I think the answer is yes. Some of us in this room are working on a mission called FINESSE, which is being led by Mark Swain at JPL. The concept of FINESSE is a dedicated space telescope for exoplanet transit spectroscopy. And to do not just tens of planets, as we may do with JWST, but hundreds of planets to advance the state of comparative planetology and to a more rigorous statistical footing. So this is an old picture of the FINESSE concept. The current concept is described here. a dedicated 75, that's not 0.75 centimeters, it's 75 centimeters, micro telescope. We're really doing this on a budget. Yeah, exactly. 75 centimeter space telescope dedicated just for transit spectroscopy with a spectrometer and a single shot that you get 0.5 to 5 microns. And so that's right, that's in contrast to JWST, which you'll have to put together your spectrum over a wide wavelength range with multiple observations. Our aim is to do high precision spectroscopy of hundreds of planets, 500, maybe even 1,000, to explore questions of planet formation and evolution, atmospheric chemistry and physics, like I said, in a robust, rigorous statistical framework. We're aiming to submit a proposal for this mission to the Mid-Size Explorer Call that's due in December of this year. The idea is to launch in 2023 to L2 with a 2-year nominal mission and doing 500 to 1,000 planets. Here are some simulations from Mike Line about finesse spectroscopy. Concentrate here on the left side. This is just different realizations of the spectrometer. I hope I'm not showing anything proprietary. Probably not. And simulations of spectra over this wide wavelength range, very high throughput spectrometer. And this is an example for, this is clear and hazy hot Jupiter and derived parameters, and showing how precisely you can measure it with these different realizations of the instrument. Then we're going to try to go with this instrument. So that's the black histograms here. So imagine getting, for example, C to O's and metallicities and clouds information for thousands of planets. I think it would be really open up a new kind of study of exoplanets. In the same time frame that we hope to launch FINESSE, the techniques of direct imaging will be advanced perhaps by the launch of W1st AFTA and the coronagraphic instrument on this telescope. W1st AFTA is something that came out of the last decadal survey. They put together a lot of different science here. And more recently, there's taking advantage of the donation of 2 Hubble telescope, Hubble quality telescopes from one of the spy agencies. The National Reconnaissance Office said, these are old technology, and the astronomers are like, God, these are great, right? So it tells you the relative amount of money that we get. Here's just a figure summarizing the hardware that's available, that's been dedicated, that's been donated. These are 2.4 meter diameter mirrors. So W1st AFTA will be 2.4 meter diameter mirror, as opposed to the on order of 1 meter diameter mirror that was originally envisioned by the decadal survey. This larger telescope diameter gives the option now of doing insightful coronagraphic imaging and direct detection of planets. And so that's the goal of that instrument, with a launch goal of mid-2020s. W1st is cool because its coronagraphic imaging will be at visible wavelengths, looking at reflected light, which is not something we've talked about a lot in my last few lectures. And so this is really going to be a new window on the atmospheres of planets. So it's doing direct imaging of planets at larger separations. And it will probably be able to see a number of planets that have been detected with the radial velocity technique. So planets around nearby stars detected with radial velocities for which we have M sin I information, which is great. And then seeing these objects in reflected light. This is a figure I just took from a paper from Roxana Lupu, including Mark Marley. Mike was probably on it. Jonathan was probably on it. Looking at the planets that would be observable with the W1st coronagraph. And taking a first look, and I thought this is really interesting, at what information can be extracted from reflectance spectra. These are ice giants and gas giants. And I thought this was really cool. So looking at different signal-to-noise ratios, including ret noise, or correlated noise length there, which I thought was pretty cool of you guys to do. This is a pretty complicated figure, but I'm just going to flash it up here. I'm not going to say much about it. Just showing, doing now retrievals on reflectance spectra, which is a totally new thing. So there's obviously probably a lot to do more here. But looking at the retrieved, for example, abundances that you can get and properties of the clouds based on different quality spectra from W1st coronagraphic imaging. Of course, we're all also eagerly awaiting the construction and operation of the next generation of large ground-based telescopes, the ELTs, generically called. The timescales for these instruments, the GMT, the TMT, the ELT, are all mid-2020s and later. The one with that would be constructed. The first is most likely to be the GMT, but the current first light is likely 2025 or later. So we're about a decade or more away from these instruments coming online. I think there are two ways these telescopes will contribute to exoplanet atmospheres. One is through direct imaging, of course, that will continue. And in the thermal infrared, it may be possible to see small planets in the habitable zones of M dwarfs, nearby M dwarfs. This is a paper by Ian Crossfield. I put a plus here, but maybe it was just Ian. Maybe it was et al. Anyway, Crossfield 2013, looking at a predicted population of planets from the Kepler mission, now populating nearby stars, and then looking at perhaps what you could do with an ELT in terms of direct imaging, contrast, separation. I'm not sure where he pulled these numbers. These are, I guess, projected performances of different instruments on TMT, for example. It remains to be seen whether that performance would be realized, but if it can be realized, showing how you would be able to reach into the inner parts of planetary systems and see and characterize more planets than currently possible with ground-based direct imaging, using the large apertures of these new telescopes and also advances in adaptive optics technology and chronographic imaging. The other way I think the large ground-based telescopes will contribute is through the technique of high-resolution spectroscopy. That's typically not going to be done from space. High-resolution spectrometers are very heavy. Putting them in space is hard. The slits are small. You need to feed them with large telescopes. So this, for the most part, will be the regime of ground-based telescopes. And so taking the stuff that Ignas Sellen's group has done with CRIRES and other people have done with HARPS and doing this now with ELTs is going to be very exciting. I'm showing here figures from simulations from one of Ignas's papers looking at the possibility of seeing molecular oxygen in the atmosphere of a habitable planet by stacking a ton of transits. But still, this is the EELT 30 transits. Well, I have to go through and look here. But the point here is that using these high-resolution techniques that we've been able to see water and methane and CO from the ground in hot planets, as the telescopes get bigger, we may be able to push to smaller planets and maybe even habitable zone planets. And Ignas has also, of course, pioneered the combination of high contrast imaging and high-resolution spectroscopy. And so this is a paper, another paper of his showing simulations applying the technique that he pioneered for Beta Pig B, and again doing this for smaller and cooler planets, potentially habitable planets. And so this is another simulation paper of his showing the detection of a 1.5 Earth radius planet with an Earth-like equilibrium temperature. If such a planet exists around, this is around, I want to say Alpha Cyn, Proxima Centauri, so this is the nearest M dwarf, late M dwarf. If such a planet exists and the instruments perform as we think they might, you might be able to do this kind of experiment in the next 15 years. Okay, so I want to wrap up with a discussion of how we will really get to the question of habitability. As I said, for JWST, the question of habitability is probably going to be on the edge of what we can do, and all of these ground-based techniques are far from being proven in terms of this level of sensitivity. And so the question becomes, how do we truly address the question of habitability? What sort of facilities do we need? And what sort of techniques are we going to use? Transit techniques are predominantly going to be used on habitable planets around M dwarfs, just from feasibility. The habitability of planets around M dwarfs is probably very different from the Earth. These planets are probably tidally locked. The real holy grail in the field, right, is the discovery of true Earth analogs, one Earth mass planets, one AU, sun-like stars. And so this is really the domain of direct imaging and future major experiments in the area of direct imaging. So I just referenced here this pale blue dot picture, right, and Carl's really amazing quote, all of human history has happened on that tiny, tiny pixel. Maybe we can see a tiny pixel of another planet around another star that has a similar kind of history. So, how are you going to do direct imaging of an Earth around a sun-like star? I cannot remember where this table comes from, but the point of this table is to calculate how precisely you have to control the wavefront for a direct imaging experiment to see an Earth. And then, if you're on the ground, how much how bright the guide star would have to be for your AO corrections to achieve this level of wavefront control so that you would see such a planet. The point being that the contrast of the Earth around the Sun is on the order of 10 to the 10, which implies an extreme wavefront control requiring a brightness, H magnitude of a guide star much brighter than anything that exists in the sky. This is a really short way of saying we will not image Earth-like planets around Sun-like stars from the ground. And so this is the fundamental argument about why we have to go to space to do this kind of experiment, why we need a terrestrial planet finder type mission. So a terrestrial planet finder was the name of a specific mission architecture that astronomers were hopeful about in the 2000s, late 90s and 2000s. That has been effectively killed by NASA, I'd say predominantly because it was seen as too expensive and the technology was not quite mature. But still, the astronomy community has pursued this idea and has had regular series of reports and studies done to continue to refine the architecture of that kind of space telescope, what technology is needed, and what's the state of the art in the technology and how much further do we have to go. So I have played a tiny, tiny role in this by serving on a NASA panel to give just a report about what NASA could do on the whole field of astrophysics for the next 30 years. Of course, one of the things we concentrated on was exoplanets and the discovery of life on other planets. But I want to just take a sidetrack here and talk about the cover of the report here. This is a great story. So we got the draft artwork from the people at NASA for the cover of this report. Enduring quests, daring visions. Apparently that's how you have to make reports in astronomy these days. New worlds, new horizons, daring quests, enduring visions, whatever. We wanted to convey that we're doing this astronomy thing for all of the world and all of humanity. And so this is the artwork they came up with. Well, this is the second version of the artwork. The first version, you see these silhouettes of these people. The first version was just awful. It had a silhouette of 4 individuals, 2 children, one person, clearly a woman, ponytail, shorter than the other person. The other person was a man holding a staff and pointing at the sky. And we got that, and it's just like, God, that is the wrong message. This is not the inclusive message that we're trying to send about who can do astronomy. Because the woman, the silhouette of the woman, she had the children gathered around her. She's like, let's listen to the man. And he's like, I've got my staff, and I'll protect you, and then I'll tell us where we need to go. And so the second version came back as this. And I don't know how much better this is, right? It's like, okay, there's a person with a bicycle. That's the message. People that ride bicycles can do astronomy too. Yeah, great. Maybe this is great, right? It's like we told the art people, we're trying to make this seem like this is an inclusive endeavor, and maybe it's not, but we're striving for this more perfect union, so to speak. And so it's like, friends can do astronomy? I don't know. I don't even know what this is trying to say. But the first version was worse, so this is better at least. Okay, in this report, though, the first chapter is about exoplanets. And so really the question is, are we alone? And this ultimately drives at doing direct spectroscopy on Earth analogs to deduce the presence of habitable surface conditions on a terrestrial planet and possibly the existence of life. There were 2 steps that we outlined. This is a very visionary document. Step 2 was actually something to map, spatially resolve and map an Earth around another star. That's in the far future. But the more realistic long-term goal is to take these kinds of spectra of Earth-like planets around other stars, reflectance spectra in the optical, resolving molecular features, and even detecting biosignature gases. Around the same time, there was a study done that was sponsored by Aura. So this study was sponsored by NASA. There was an Aura study also studying the question of how we would take spectroscopy of Earth. And we all came to the similar conclusion that we need something on order of a 12-meter space telescope. To do this, we may be able to take images of solar systems like this. This study was led by Julianne Dale Canton and Sarah Seeger, co-chairing and producing this report, which you can find on the archive as well. All of these studies are leading towards a concept for a space telescope that's now known as LUVOIR. And I have to say that it was our committee that's to blame for this terrible acronym. Large ultraviolet optical infrared telescope, which, if you have a terrible ear, sounds like the French word for laundromat. We have any French speakers in here? French word for laundromat? Come on. Kristen? Lavoir? It's like lavoir or something like that? Lavoir. Yeah, so we're trying to kind of got to get like more of an accent. Like if I put on a beret, I could probably say this better. Right, so lavoir, it's like French for washateria. Anyway, lavoir, it will have a better name if this is going to go forward. But this is the current concept, is a space-based telescope, large aperture on order of 12 meters, segmented primary mirror, because getting something like that into a fairing on the top of a rocket is going to require folding it up like so much origami in JWST. So this has got its own challenges. How do you build a coronagraph for a segmented telescope that does 10 to the minus 10 contrast? But anyway, this is the concept that people are working on now. There's another study being conducted right now in the context of preparing for the next decadal survey. 4 major missions are being studied by a number of different teams. LUVOIR is one of the studies that's being done, led by Deborah Fisher and Bradley Peterson. I'm on this. Mark Marley's on this. Mark is the chair of the Exoplanets Working Group for this mission, so if you have questions about what's going on, you could ask him or me a little bit. There are a couple of other missions being studied in the context of our science. This other one, known as HabEx for short, is also interesting. LUVOIR is thought to be, the vision is a Hubble or JWST type telescope. That is a general purpose facility, but also with specialized instruments specifically for direct imaging spectroscopy. HabEx is more of a focused instrument. So this is probably a smaller telescope with just coronagraphic imaging capabilities. So all 4 of these missions are being studied in preparation for having a fleshed out design and cost so that information can be used in the deliberations of the decadal survey to set the course for astrophysics for the next, actually, decades. So there's a link here where you can find more information about this stuff. My final slide for my 3-hour lecture this morning is a screen grab of yours truly sitting straight up in front of the committee of the House of Representatives, the Committee on Space, Science, and Technology. I had the privilege of testifying before this committee about the search for life on other planets about a year ago. And so I didn't do such a great job in the questions. I thought my statement that I prepared was okay. The thing, you can read the statement that I wrote, which is a little bit longer. I think it really outlines in a clear way, this vision for the future that the community, this is not my personal vision, right? I'm just representing the community's vision for the future of taking spectroscopy of Earth-like planets. If you do watch the video, try to find the place in the video where I roll my eyes at the chair of the committee for asking a question that I had no idea how to answer. I think the question was, what's the chances that we're going to find life on another planet in the next 10 years? And I was just like, anyway, if you watch the video, it's in there. 1 in 5, though, I thought. Yeah. Well, because I'm like going through these things in my head. I'm like, well, I don't want to tell him the truth because he'll say, why? What's the point of funding all this crap, right? If you're like, it's 1 in 100, he'd be like, no money for you. Jonathan Lunine says we're going to find whales on Europa. Let's give him the money, right? So I'm like, well, I don't want to say the truth, which is that it's probably a low chance, but then I also don't want to get his hopes up. And so right there on the spot, right, I'm like, what the hell's the right thing to say? So the truth is I didn't roll my eyes. I looked up at the ceiling. I was like, God, are you there? What's the right answer? But the people watching at home said it looked like I was rolling my eyes at the chair of the committee. Anyway, that's my lecture. Thanks so much for your attention. I'd be happy to take some more questions and talk later too. No more questions, actually. Kristen, yes. Mm-hmm. Mm. Mm. Mm-hmm. Sure. Yeah. Mm-hmm. So one thing that's happened, say, in the last 5 years since the failure of TPF is this: our community, I think, has wisely realized that we need to search for synergies with other fields of astrophysics and other even planetary science. And so I think that's really what the LUVOIR concept has come out of that realization, or the HDST concept has come out of that realization. Is that if we're going to have a new large flagship space telescope, it should be able to do a lot of other things so that we get buy-in from as broad a community as possible. And so I have more optimism now because I think people in the astrophysics community are also excited about that, because I think it's unlikely that astrophysics beyond exoplanets would on its own justify a 12-meter space telescope. That's my feeling. But if you have the potential to search for life on other planets, that's a driver. That's a science driver that the public can get behind. And so, the unifying thing is like building an observatory that can do many things, but is also optimized for what we'd like to do, perhaps with some few trade-offs. And so, like, for example, the segmented mirror of LUVOIR is to get us to 12 meters. The original TPF coronagraph mission was a monolithic 8-meter elliptical mirror that you could turn sideways and fit into a fairing. But that thing wouldn't be a major advance. Such a telescope wouldn't have the collecting area, for example, to be a major advance in the field of extragalactic astronomy. Whereas LUVOIR, with a large 12-meter, roundish mirror, would have that. So I think that addresses what you're saying. Is the community is thinking in terms of that, and I think that's very wise and gives us hope for the future. Lunch.